Hi everyone, welcome to GEMCHEM. Now today's video is on alkenes part 9 video, and here we will deal with an important reaction of alkenes, which is oxymercuration and demercuration. Now before starting, if you have not watched the previous videos on alkenes, please do watch it. I will give the link in the description box as well as the I button present above this video. Now let us start today's video. Now, an alkene when treated with mercuric acetate in presence of water produces mercurial compound, and this hydroxymercurial compound on reduction with sodium borohydride under alkaline condition yields an alcohol. So this is a basic process of conversion of an alkene to an alcohol. Now we can observe this step. That is, this alkene on reacting with this mercuric acetate, that is HgOAc whole 2, and in presence of water and THF as solvent produces this kind of compound, where OH gets attached to this carbon and HgOAc attached to this carbon. Now on being reduced using NaBH4 under alkaline condition, demercuration occurs and we get a alcohol compound. Right. Now the first stage is known as oxymercuration, as it involves addition to the carbon-carbon double bond of OH and HgOAc. Then in demercuration, this HgOAc is replaced by hydrogen. Now the reaction sequence amounts to hydration of alkene, right, but is much more widely applicable than direct hydration. The two-stage process, that is this, is advantageous. And why is it so? Because this two-stage process is fast and convenient, takes place under mild conditions and gives excellent yields, often over 90%. So we see that there is no existence of any harsh conditions. These two reagents are mild conditions, so this is advantageous. Now the mercury is recovered as a ball of elemental mercury at the end of the reaction. So the alkene is added at the room temperature to an aqueous solution of mercuric acetate, diluted with solvent tetrahydrofuran, that is THF. Then the reaction is generally complete within minutes. And so the organomercurial compound is not at all isolated, that is the intermediate, but is simply reduced in situ by sodium borohydride. And this reaction is highly regioselective and gives alcohols corresponding to Markovnikov's addition of water to carbon-carbon double bond. So it follows Markovnikov's rule. Now in the last video, that is alkenes part 8 video, we have already discussed about Markovnikov's rule and anti-Markovnikov's rule. You can watch it. I will give the link in the description box as well as the I button present above this video. Now see, what does Markovnikov's rule state? It states that negative part of the addendum, that is the substrate which you are adding, its negative part will go to that carbon which is poorer in hydrogen. So we see here, first example, let us see this carbon has one hydrogen and this carbon has two hydrogen. So let us draw the hydrogens. So this carbon has one hydrogen and this has two hydrogens present. So we can see that the negative part, that is OH minus, is getting attached to this carbon because there is less amount of hydrogen present here. Similarly in this case, here there are two hydrogens and there are no hydrogens. So OH gets attached to this carbon. Similarly, if we observe for this one, we can see this has no hydrogens and the down portion, that is this one, has one hydrogen. So the OH gets attached to this carbon, right? Now we will go for mechanism. So let us see. This is the alkene, and here a basic electrophilic addition of the mercuric ion takes place. So what is the electrophile? HgOAc plus, right? And we can consider it as soft base and this as soft acid. So a reaction between an acid and a base which are both soft takes place very easily. And if there is no kind of rearrangement or stereoselectivity, then there is no formation of classical carbocation. There is a formation of cyclic mercury bridged carbocation. Okay, let us see. This is our alkene. Now when mercury gets attached, HgOAc, and this gets attached, and the charges here is also delta positive and here it is also delta positive. Now comes the water. Now this water has lone pair within it. So this lone pair attacks this portion, that is, this is positive and this is lone pair that is having negative charge. So ultimately what we get is COH, and this bonds open up, so we get HgOAc. Now there is an observation which helps us to understand that this is okay, our mechanism is okay. Suppose if we take this kind of thing, there is a pentene ring, and if we react it with HgOAc whole to water THF, then the ultimate product which is obtained is just like this. That is, H comes up, OH comes up, CH3 is here, and down there is HgOAc. So this supports the orientation of addition and shows that the nucleophiles becomes attached to more highly substituted carbon, and it may be anticipated that in transition state for nucleophilic attack, carbon mercury bond breaking exceeds the formation of carbon oxygen bond making. That is, transition state is potential carbocation. Now although all these things are okay, but demercuration is slightly problematic. That is, free radicals have been proposed as intermediates, but it is not really understood. Now see our HgOAc. Okay, now when NaBH4 is being added in presence of OH minus, then we get our HgH. Okay, and this often undergoes homolytic cleavage. That is, one electron comes here and one electron goes here to form ultimately R dot plus dot HgH. Now this further reacts to form RH plus Hg dot dot, that is 2 electrons. That is, this bond breaks. Okay, now whatever the mechanistic course of demercuration, it is not in general stereoselective, and thus despite of stereoselectivity in the first stage, overall process is not in general stereoselective. Sometimes there is a problem, that is, there is a rearrangement taking place, so we will deal with it in the next example. Now see this one. Demercuration is being taking place and we are getting 3 different products. As it proceeds via free radical mechanism, so there is a 3 product formation and can be explained from one particular free radical parent. So let us see. Now this one, on reacting with NaBH4 OH minus, it produces this kind of thing. That is, here H is up as shown and OAc is down, and this one there is a formation of HgH bond. Okay, now this further cleaves and we obtain H here and a dot here, and this comes here as usual, and here there is hydrogen, and here there is OAc, and here HgH dot. Now see, previously we had seen that this bond breaks and we get this kind of thing, R dot and Hg8. So same thing is occurring here. So now this is our parent free radical. Now we will deal with it to see what products are being formed. So let us see. Now if we take the parent free radical, that is this one, and here is hydrogen and here OAC, here hydrogen, and there is a dot, that is free radical present here. Now we know that there is a dot HgH, right? So now what happens? This bond cleaves, that is the bond present here is homolytically cleaved, and this hydrogen comes here. So now what happens? Ultimately first product is being obtained, that is here a hydrogen, another hydrogen, here is a bridge, and here H, and here is OAC. Now see, this product corresponds to this first product. Now we will go for the next one. Now in the next case, this opens up, this comes here, and this free radical goes here. So ultimately what we obtain is this kind of thing. That is, here is hydrogen as usual, here is OAC, here is hydrogen, and there is a bond formation between these two carbons, this one, and here a free radical, and this bridge remains as it is. Now what happens? Then again we add Hg, H, and this one is dot. So again this one cleaves homolytically, and this hydrogen comes here with a dot. So ultimate product in this case is this one. That is this same thing, this one, here hydrogen, and here OAC. So this is our product. So see, this is the second product which is being obtained from the same parent free radical. Now we will deal with the last one. So first we will draw the parent free radical, which is this one. We know here hydrogen up, here OAC down, here this one up, and here there is a free radical, and here is a double bond. Now what happens? This whole bond migrates to here. Okay, so here there are 2 electrons and this bond migrates to here. So ultimately what we get is this one, that is this part remains intact, this one, then H, OAC, this hydrogen, here there is a free radical, here there is a double bond, and this bond has come here. So this one, right? Now what happens? We again give Hg dot H, then this cleaves homolytically, and this hydrogen with dot gets attached to this radical. So ultimately what forms is this one, that is this one, and this one, and here there is a hydrogen to hydrogen comes, so free radical gone, and this is H, and this is OAC. Now if we consider this part as the bridge, let us consider this part as the bridge, then on just rotating the plane we can write the structure as this way, that is this way, and this is the bridge containing H and OAC, and the double bond present in this side. So basically we are considering this 5-membered ring in this plane and the other blue portion as our bridge. Okay. So ultimately we are obtaining our third product which is required. So this is our third product. Now we will go for this one. So see, now we will see for this reaction what happens. Right, there is a formation of 2 products. So first of all we will write first step. that is here formation of OH and here formation of HgOAc, right? And here there is a double bond. Next step is this one, that is formation of cyclic mercuric intermediate. So here there is HgOAc plus and here OH HgOAc. Now see, when this oxygen attacks this one, this carbon, then this opens up, so we get the product as this one, that is here HgOAc, here O and here O, and this is HgOAc, and this forms this one. But if this OH lone pair attacks this carbon, then it opens up like this, so we get another kind of, that is this one, here oxygen, HgOAc, and this is HgOAc. So this gives this product, just written in different manner. So this is how these are two formed. Now we come to this one. See here, there is slight difference in the conditions. We can see that here we have not used acetate, that is HgOAc. We are using CCF3(2), and we are using alcohol rather than water. So what is the reason? This reaction is mainly used as an example of Oxymercuration and Demercuration to form ether. So we can see that there is a formation of ether. Now basically what happens, if we take HgOAc, then attack of OR will not be favored and OAc will attack. Whereas if we take this CF3, then it is less nucleophilic than OR, that is alcohol. So there is formation of a ether. So let us see the mechanism, then it will be more clear. Now see, if we take this, then the first thing which will be occurring is formation of cyclic intermediate. So this is the one, here there is a hydrogen, here is a CH2. So this Hg and OCO CF3, then this ROH attacks, this one attacks this center and this opens up. So ultimately we get this one and ROH plus, this is attached to oxygen actually, and then this is CH, CH2, HgOCO CF3. Then the reaction proceeds as usual and we get the ultimate product after this reduction, that is this one. So what is important? This is important technique to obtain ether, and ROH and OCO CF3 are in competition to react with mercury bridged carbocation, but because of strong minus I effect of CF3 group, ROH is more nucleophilic than it. So ROH attacks the mercury bridged compound, that is carbocation, to yield an ether. Now if we take mercuric acetate, then it may attack the mercury bridged carbocation as it is more nucleophilic than ROH, and it will lead to acetate rather than ether, and it may ultimately yield alcohol, not a ether. So this important reaction is a result of formation of ether. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.